I'm going to tell you about Einstein's gravity, and the whole new theory of gravity that he invented. But you have to put it into the context of what he built on, and what you get taught in high school and in most physics courses that are the beginning physics courses is you learn about Newton's theory. And why would Einstein bother with anything that was already working so beautifully? It got us to the moon. I mean, of course, Einstein was gone by the time we got to the moon, but it doesn't matter. Why would he bother to make another theory of gravity if you had a theory that worked so exceedingly well already? And that is part of the challenge here. What happened is that in 1905, when he discovered special relativity, he already realized, or the world realized, that there had to be some way to make things not instantaneous. In other words, information couldn't travel from one place to another, even in a gravitational field, instantaneously. And that kept him worried. And in fact, very shortly after the special theory of relativity got formulated, he began to think about gravity. How would you reformulate gravity so that it was consistent with the ideas of finite speeds of information, and also deal with the problems that change everything in physics when things go near the velocity of light, and we have very large masses and very large velocities. And that's what the origin of the general theory was. And he worked on that for many, many years. And by 1915, which is just about 100 years ago, he came and involved this very elegant theory that'd be named general relativity. It was really a new theory of gravity. And I want to give you a little feeling of that theory before we get started with gravitational waves. And the way you want to think about it is in this picture. This picture is, here you have to imagine a little first how Einstein must have thought about it. Imagine a network or a framework of poles you stick up like a jungle gym. I mean, many of you played in jungle gyms when you were kids. But where you make a thing which has 3 coordinates and you have bars that are all separated and they connect 1 meter apart everywhere. And that's sort of the way you imagine this and the way Einstein was thinking about it. And then he also, when you imagine this framework that's set up, you put a clock at every intersection point of the different bars that you've made. So you have a zillion clocks and you have to synchronize them all. And you do that by looking at them all and going with your clock and saying, oh yeah, let's set the time on each one as you go along. And that's what you set up. And now this picture shows what happens to that jungle gym, in effect, in the idea of Einstein's, the way he was thinking about gravity. Because here is some piece of the jungle gym, quite distorted. And by the way, there are clocks everywhere. They're not shown here. And they also get distorted in the following sense. They don't all keep the same time anymore. And what's happened is, here's the sun that's been put into this system. And you can see it changed the shape of space, but it also changed all the clocks as well. And here's the Earth, and it changed a little bit, the space around it, because it's not as big as the sun, not as big a mass. And this is, in fact, the conception that Einstein had of the way he was now going to look at gravity, and he wanted us to look at gravity. Namely, that what masses did is they distorted that beautiful Euclidean framework that you set up with the clocks that were all synchronized, and it screwed up the clocks and it screwed up the space. That's what it did. And now what happens is the curvatures in space and the reduction, the changes in the time, the clocks run more slowly near these big masses than they do for far away. Combine them with what the space now and the clocks together tell the Earth how to move around the sun. There's no longer a gravitational force. That's the big change. And in that framework, you can have gravitational waves. And I'll show you what they look like. They look like this. And they are generated by the same thing that the electromagnetic waves are generated by. Namely, these waves get generated by accelerated masses. You accelerate mass, you accelerate the sun, you accelerate anything, and it generates these gravitational waves. And it can't just be any old acceleration. It turns out spherically symmetric accelerations, things that are completely spherically symmetric, don't make gravitational waves. They have to look a little bit asymmetric. They have to have, in the fancy word of physics, they have to have a quadrupolar nature. Namely, a thing that two things crashing together, for example, will make gravitational waves. A balloon that expands uniformly and contracts uniformly will not make gravitational waves. or things that are orbiting around each other, that sufficiently has enough quadrupole nature so that it will radiate. So it's a non-spherical acceleration that makes gravitational waves. And right in the first paper that he wrote, he said that these waves will move at the speed of light. They will move just the way as electromagnetic waves will. And here is what a gravitational wave will do. And I'll start this up in a minute. They're transverse waves, meaning if they travel at the velocity of light, they do their dirty work perpendicular to the direction in which they're moving. And now I want to turn on a little bit of an animation. You don't get dizzy with this, but the way you want to think about this animation, this is a picture of what a gravitational wave will do if you're standing here. If you can see this red square around that dot, well, these dots, think of them as places that label space, okay? And now what happens, you'll notice that this motion is sort of interesting. What it's doing is it's shrinking space in one dimension while it's contracting space in the other. And it keeps alternating that because it's an oscillating wave. It's coming in, it's either going into the screen or coming out at you, okay? And now there's another attribute of this thing which is very important to recognize, which is critical in the business of being able to see how you might detect these waves. And that is that you'll notice that, let's say, take you again. Here you are. And here, these two dots right there don't move as much as this dot and that dot. In other words, the amount of motion of those dots is a function of how far they're separated. And that picture then, at any one instant, is a picture of constant strain. And most engineers know what a strain is. I mean, you experience that when you pull a rubber band. And in fact, if you want to show this to your kids, just do the following. Take a rubber band and not stretch it, and put every quarter of an inch or whatever, every centimeter, make a little mark on the rubber band and pull it apart. And when you do that, that is also a motion of constant strain. And what does that mean? It's the change of the position of an object is proportional to their separation, or the change of the position divided by their separation is a constant at any one moment in this picture. So the field quantity, the quantity that you want to be looking at, the thing that tells you about the strength of a gravitational wave, is the strain. And we'll talk about that a lot more in a minute. So I'll stop this thing. And in 1916, in 1915, he wrote these wonderful equations, which were, in fact, the Einstein field equations, which, as I said, we celebrated last year. In 1916, he wrote another paper in which he does what's called an approximation calculation. The huge field equations he had were very complicated to solve. People really only know how to solve them now with computers. I mean, they can do it completely. But what Einstein did is, all of us would do, he tried to make it so that you make it linear, looked at the gravity when it was small, and that was what he did in the 1916 paper. And in that paper, he showed a whole bunch of different things. He showed what I just told you, the gravitational waves, and he says something really quite remarkable in that paper. It was in German, of course, and what it says, what this is I'm not trying to ask you to understand the equation. I want to tell you what it is. It's that here is a change in the aspect of something which is moving, and here he's trying to calculate how much power is moved, how much energy is being taken out of the system and effective per time by this motion. And he says in here in German, which those of you who can read German will read, but here's a translation of it. He says this quantity A, so in any case one can think of A, that thing, will have practically a vanishing value. In other words, he says, put the numbers into this thing, evaluate the equation, and you will find out it's absolutely zilch. It doesn't do anything. And now I've asked people who have been experts in the science papers of Einstein, and there are a whole bunch of people who do science history, to find the place where he did these back-of-the-envelope calculations where he might have come up with this statement. And they haven't been able to find it. I mean, you don't find it in his notebooks, and you don't find the back of envelopes anymore. So there's no record of it. So I took a very presumptive step and made myself Einstein for the moment of this lecture. And he must have done both of these things is what he might have done. For example, he might have considered two trains colliding with each other. That's something they could have imagined in 1916. And here is a formula which I'll just describe what is in here. And this is so you and I both can estimate anything we want about gravitational waves. You don't need any more than this. What is in this formula is H, which is actually the strain. That is the strain. H is a symbol he used for that. And what is it proportional to? It's proportional to things you know. For example, this is g, which is the constant you'll find in Newton's equations also. It's the strength of gravity. It's the mass of the system that's doing the colliding or the motion. It's divided by the distance you're away from the source. That's the distance you're away from the source. And it's divided by c squared, which is the velocity of light squared. That quantity, that right there, the gm divided by r c squared, that quantity is a very important quantity. It gives you the strength of gravity in an absolute way. We, you and I, all live in a place where that gm over rc squared is about 10 to the minus 10. Now, those of you who don't know exponential notation, I'll be using it a lot. When I say 10 to the minus 10, I mean it's a decimal point with 9 zeros and a 1. Okay, that's what I mean by 10 to the minus 10. You're going to have to live with that. I don't want to get it right and say point, that's just too boring. 10 to the minus 10 is a wonderful way to encapsulate that, so you'll have to live with it. And so it turns out, at a black hole, which we'll talk about later as we get into this thing, that number is 1 at the edge of a black hole, at the place we'll talk about later. So Einstein's equations work over a dramatic range of strengths, field strengths. Certainly you and I live in 10 minus 10, and a black hole is 1. People are doing experiments here in Adelberger's group where that is even smaller, 10 to the minus 5 of 10 to the minus 10, so 10 to the minus 15. It's a huge range of gravitational field strengths, and those equations that he saw and pure thinking in 1915 work over that huge range of energies. So that's the first piece of making h, and then what's in here is the velocity of what's doing the moving divided by the velocity squared divided by c squared. So let's just put some numbers into that formula using, for example, what Einstein must have done. Here's 2 trains that have smashed into each other. And let's pick them as having about 10 to the 5 kilograms each. That's the mass that's moving. Even, well, nowadays, we probably don't go that fast with trains anymore because we don't know how to make trains anymore. But in 1916, they probably went at 100 kilometers per hour. Okay? You put that in. And the collision took 1/3 of a second. That's not completely crazy. And you have to go far enough away to see this radiation. You can't, because if you're too close to it, you'll see Newton. That's all you'll see. But you go far enough away, you'll see Einstein. And you have to go out in a range, a distance far enough away, so that you can see the radiation itself. So you have to go 300 kilometers. That's about with these numbers. And what you wind up with is a strain that's 10 to the minus 42. Now, that is truly a small number. That's infinitesimal. Okay? That's point, I'll just say it one more time. That's a point with 41 zeros and then a 1. Okay? It's just vanishing. So no wonder he made a statement like that, this will never have any significance. So the other thing he might have thought about is, well, let's look at things that, not try to measure something that's on the Earth, but there must be systems that, like the binary star system, and we'll see those a lot in a minute. And in his day, there were known binary star systems that sort of had masses of 1 solar mass each. They had an orbit that took 1 day for them to go around. Now, he probably didn't know about the galaxy. Nobody knew about the galaxy, but let's put it at the center of the galaxy. That's 10 kilo light years away, okay? 10,000 light years away. And then you get a strain, which is actually, it's still a mighty tiny number, 10 to the minus 23, with a period of half a day period. It's twice the frequency of that. And, but that is, as you'll see when we get talking about real gravitational waves, is not a tiny number anymore. But the way he couldn't have measured it, but he could have maybe looked at the thing and watched it through a telescope. That was probably the thing he might have thought of. And how long would it take so that you could see that this was losing energy to gravitational waves? That's something he could have done. And so he would have wound up with something that took 10 to the 13 years before these 2 stars got half the distance between them. That's how, when you lose gravitational energy with 2 things that are going around each other, and we've been talking a lot about that, 2 things going around each other, there's a very persnickety thing that happens. They go around each other, but they get faster and faster as they get closer and closer. That's what they do. And so you would have seen, he would have calculated, that took 10 to the 13 years. That's more than the age of the universe, although the universe was not known about in those days. So it looked pretty hopeless. It really did. And I don't blame him for writing that very negative and dismissive sentence. So, what's happened since? Two things have happened since. Technology has changed dramatically, and the other thing that's changed is discoveries in astronomy. And I'll show you one that is most important. And by the way, I just want to correct something that David said, which is it's perfectly fair that he should say it. We were not, this is not LIGO, was not the first to ever get real evidence for gravitational waves experimentally. It's these people. And these people, this is a graduate student at the University of Massachusetts, Richard Russell Holtz, and here this was a professor at the University of Massachusetts in Amherst. They both now at Princeton. This is Joe Taylor, and they did something really amazing. I think to me it's as wonderful as any other thing that ever was done in astronomy. What they did is they found, and here's how they did it. They found it by using radio telescopes. You don't see a thing with a radio telescope. You can hear things with a radio telescope, but you can't see it, you know? And so they listened, and they found a place where they found something that was going brrr like that 17 times a second. And that was this thing. It's a pulsar. It's a neutron star. They found this. That's in a search they were doing for neutron stars all over our galaxy. But this one was kind of strange, because what it would do, it would go 17 times a second. It would get a light pulse, or radio pulse would go and hit the radio antenna. And then sometimes it would be a little faster than that, and sometimes it would be a little slower. In other words, as this thing was moving toward us, or the radio dish, it would be a little faster. When it was moving away from the radio dish, it was going a little slower. Much the same as when you hear a cop car, following you, and as they pass you on the highway, it's a high-frequency siren as they're coming at you, and then when they move away from you, it's a low frequency. It's a Doppler effect. Most of you know about that. So they divined from that, just from listening to the pulses from this thing. That's all they had. They couldn't see a damn thing. They decided it had to be another star that was going around it. And so these two things were going around each other. And what they discovered very quickly, it took them, and this is the time, this is sort of talk about persistence in doing science. They found this thing in 1973, and they were still working on it in 2000. And they kept following this star system on with the radio telescope, and they found out that indeed they could solve all from just the way the pulses came in and they changed. They could find the masses of the two stars. They could find out that the thing was moving around, that the ellipse that this ellipse they have was actually turning, which is what you expect in general relativity. They could see the bending of the radio waves from that star as that one was getting in its way. And, most important, they discovered that this system was speeding up. In other words, what was happening was this time of going once around every 8 hours was getting shorter and shorter. And that's what this picture, that plot is all about. This is epic. This is, time, evolved time since 1975 to 2000. And this is the change in the time it takes to make one revolution. And it's getting shorter and shorter. You see there's negative signs here. It's getting shorter and shorter. And the dots that they have here, those are the dots that they measured of the change in the period of the orbit. It's getting shorter. And this is the theoretical curve if this thing was losing energy due to gravitational waves. I mean, it's a dead ringer for it. And that was, as far as I'm concerned, the first real evidence that there were gravitational waves. And it was a very important moment because there had been endless discussions in scientific community about whether the gravitational waves that Einstein had predicted were real or not. People made calculations, sometimes some people, even Einstein himself in 1936, had come up with a calculation with another scientist. They published it wrongly. They made a mistake, but that happens all the time. And they said, no, gravitational waves, they had to come to the decision that gravitational waves were just not real. They didn't carry any energy, they didn't carry any momentum, they didn't behave in any way physically sensible. And then later on, people began to doubt this, and it took until actually this experiment to really prove that gravitational waves carry energy. There was endless discussions about this. Okay, so the next step in all of this is a little earlier than what I just showed you, but it's as important. This man is Joe Weber, and he was a member of a meeting in 1957 called the Chapel Hill Conference of General Relativity, in which people were really discussing this issue, and a lot of very famous people were there. Dick Feynman was there. He, in fact, listened to the whole conference for a while and said, "This is all mathematics. You guys got to do some physics. Get to it," you know. And but they did get to physics, and I'll talk a little more about that as I go along. And one of the things they got to is that Joe Weber and John Wheeler, who was a physicist at Princeton, came up with the idea that maybe one ought to detect gravitational waves by that picture that I showed you, that stretching of space. It turns out the way they reasoned it, it also looked like there would be a force, a differential force that a gravitational wave would make on matter. And what they invented was this thing. Now, the guy in the picture is Joe Weber, and he was a standard man, not, I think, 5'10" or something like that. This is a gigantic piece of aluminum. And the idea was, and you see him before I tell you the idea, what he's doing there, he's soldering to that big piece of aluminum, he's soldering little strain sensors, things that will give a voltage out when that bar starts singing and starts moving. And so the idea was that a gravitational wave would come along, go through the bar, and stretch it a little bit, compress it this way, stretch it that way, and that would start the thing ringing, and it would ring on just as though it had been hit by a hammer. It was a very straightforward idea. It was not such a clever idea to think about how it worked. That was a problem for me, by the way, as we'll get to later. But on the other hand, so what happened is Joe set this up. This is Joe Weber, and he set this up in his lab in University of Maryland, and then he had another one of these in a golf course 8 miles away, and he kept seeing things that were coincident. And he saw something of the order of 100 events per day that were coincident between his bar in the lab around his office and that place he had set up in the golf course 8 miles away. And he got very interested in that. And of course, he didn't say it was gravitational waves right away. But what made him say that was a third piece he did. He took another one of these bars and put it in Argonne Laboratory in Chicago, which is about 800 miles away from Maryland. And then he had 3 things to look at. And those 3 things would give coincidences on the average of 1 or 2 per day. And in 1969, he published a really quite dramatic paper saying he had looked at everything that could do this, and he was now convinced that he had detected Einsteinian gravitational waves. And that caused the whole world, a lot of people, to at least 4 groups in the United States, a group in Russia, several groups in Europe, to start doing the experiments. And by 1972, most people weren't seeing anything. And that was a very big blow to everybody. I mean, he had made a very dramatic claim. A lot of people did it exactly the way he did it, and they saw nothing. There were some people who did it better than he did, and they didn't see anything. And that was a serious issue. And I was at that moment asked to teach, not at that moment, but about a little earlier than that, I was asked to teach a course about general relativity at MIT. As I explained to David, what happened is that I had started a lab at MIT on gravitation and cosmology, which were topics that I thought were interesting. Nobody was working on that at MIT at the time, and that field had been relegated to mathematics, and it looked sort of not interesting to physicists. And so they asked me to teach. The head of the department came to me and asked me to teach a course in general relativity. Of course, I didn't know any general relativity. I mean, that's what I knew. I knew a lot about the experiments, but I didn't know hardly any of the mathematics. I didn't know tensor analysis. I didn't know any of the fancy stuff you really had to do. But I couldn't say I didn't know it. Okay? So I was sort of in a situation where I was a day ahead of the students. Most of the time, I was a day behind the students. It didn't matter. But anyway, so we had, thank God, a set of convivial students who were willing to let this somewhat blustering character allow them to teach them. But nevertheless, we got along, and in the middle of it, they asked me about Joe Weber's experiments. Now, this is before he made his big statement, but it was close to the same time. He was already, at that time, giving talks at physical society meetings, saying that he was implying that he was seeing something that looked like gravitational waves. He didn't finally have the courage until 1960. The course was in 68 and 67, and his big statement was in 69. And so I had a problem, and when the students asked me, explain to us, how a gravitational wave interacts with one of Weber's bars. And I couldn't really do it because I didn't believe it. I didn't understand how the wave actually pushed on the bar. That was my problem. I thought, here was my problem. I'd been so deeply immersed now in learning general relativity that I felt there were no more forces. Forces were an artifact of Newton. And I want to see how this thing worked geometrically. And it was such a beautiful idea to do this all geometrically like I described to you. And here was this thing, very ugly thing that was being pushing a bar around. Didn't seem right to me. So I wanted to explain this some way in a geometric way. And so I spent the weekend thinking about that. And I came up with something which later turned out to be reasonably important. And it was, why don't I explain it as put a mass, one of those spots, those dots I showed you, put that over here and give it a clock, and put another one over here and give it a clock, and then send a light signal from this mass to that one and have it reflected and come back to this mass. So I do all my measurements all in one place. I don't get messed up with having to worry about how you transfer measurements from one place to the other. It's all done in here. Send the light beam back, come back, and you measure the time it took for the light beam to come back and forth. Okay? Very straightforward problem. You can do it just like special relativity. It's a simple problem to pose. And now what happens, along comes a gravitational wave down on this system, and what it does is it changes that time. And that was, it's shorter and longer than it was without the gravitational wave there. Looks so gosh darn obvious to me, okay? And so I gave it as a problem, and everybody did the problem, and they all got the right answer, and everybody went away happy, and that was it. Okay. I put it aside. I didn't think about it anymore. And then when 72 came around, and nobody had seen any of this, I began to think about this as a more serious thing. It was, let's put it this way, Einstein would have called that a Gedanken experiment, the one in that, the thing in the teaching the course. But I want to convert that Gedanken experiment into a real apparatus. That's a very different thing. And so let me give you the germ of the idea, and that's what this little animation will show you. So what you're seeing here is you're seeing a laser. That's not a laser, but think of it as a laser, okay? And it'll send out a light beam hitting this beam splitter, which is a device that splits the light, so half of it goes to that mirror as transmitted, and half of it goes to this reflected. And then the lights come back to this thing, and here's a photodetector. And let's see what happens if you make it so that the light spends exactly equal time in this arm and that arm. By the way, those of you who know, this is called a Michelson interferometer. It was designed back in the 1800s. Okay? So here's what happens. Yeah, it works. Wonderful. And so here's a light beam, but now the red shows where the intensity of the light is, but this wiggly thing is the electric field in the light. It bounces from the light, bounces from these mirrors, and now you'll notice that if these times are the same, the two fields cancel each other, and there's no red here. There's no light hitting the photodetector. And now what happens is the animation will start moving this mirror one way and this guy in and out. So there's this push-pull thing that's going on. That went on in that. And you'll notice that every once in a while there is light at the photodetector, especially when you have moved those mirrors. And by the way, what you've now done is you've made one arm a little longer and another arm a little shorter. And now all of a sudden that cancellation, which gave you no light at the photodetector, is spoiled. It's very straightforward, and that is the basis of the whole idea. There's no more than that. Okay? That is the idea for how you detect gravitational waves. Now, the trouble is when you get to actually wanting to do it, okay, you get into a problem, which is the following. And we didn't know that at the time, and neither did Joe Weber. Joe Weber, if you want to know what he was detecting a strain which later we figured out was about 10 to the minus 14. Now, that's what he was measuring. And by the way, later on people made the calculation that if he had been right, he would have wiped out the galaxy, our galaxy, in about 1 million years. In other words, you would have converted every mass in the galaxy into a gravitational wave energy to get such a strong amount of strain. So that was another, you wouldn't, as a theorist, you could argue that Weber was seeing nothing. I much prefer that other people who were doing experiments were seeing nothing. That would be, okay. So, but this is when people like Kip Thorne and a lot of other people began to really calculate what kind of gravitational waves you might expect and how strong they might be. The number that they felt you had to get to, that value of h you had to get to was 10 to the minus 21 and smaller. Now, when you convert that into the dots in that picture being 4 kilometers apart, which they will be in LIGO when we get to LIGO, that means that the motion that you're talking about at the endpoints, those dots that were moving quite violently when you had that animation, is only about 4 times 10 to the minus 18 meters. Now I want to give you a little feel for 4 times 10 to the minus 18 meters. And that's important that you understand this. That's when the fat gets in the fire. It's not in the idea. The idea is simple. But now what you have to do is try to, let me give you first a feel for it. So you start with a meter. In the United States, we don't deal with meters, we deal with 3 feet, okay? It's close enough. And so you divide by the first 10,000 and you get a hair, okay? That's easy because we all have hair, most of us do. And then you divide that again by another 100 and you get to about 1 micron, or a visible light, which is about half a micron, or 10 to the minus 6 of a meter. And you still can experience that. You can do beautiful things by looking at a light through a pair of fingers, and you'll see little bands. It's very easy for you to establish that light has a wavelength of about a micron, or half a micron. You can even get to the next step here, which is that divide by the next 10,000. You get to the size of an atom. And you can prove to yourself and your kids how big an atom is. It's real easy. The way you do that, that's about as far as we can go, though, that you can prove to yourself. You take a medicine dropper, and put a little bit of oily stuff in there. I don't care what, any vinegar, oil, or peanut oil, whatever you like. Or gasoline. I don't advise that, but that'll work too. And then you look at the medicine dropper drop, and you measure it as best as you can with a ruler, or maybe millimeter in diameter, whatever it is, and you can calculate the volume of the drop. That's real simple. You measure that because you know a little arithmetic. You know how to get from the dimensions of the diameter, you know how to calculate the volume. And then you drop it into a bucket or into the bathtub or into the sink. It's just full of water. And you'll notice as you drop it in, it spreads out. And you'll see the edge because the colors are different in the water. And you measure it with a ruler. You measure sort of the size of the area. You do that. And then you need one other thing. How high is that thing? And that's going to be 1 or 2 atoms. So that's still something within your capability. And and you'll find out that when you do the calculation, it's a nice experiment to do. You should do that with every kid in the world. It's just a great thing to do. Then you wind up with 10 to the minus 10 meters for the size of an atom. Not 1, 2, order 10 to the minus 10. Now you get into the regimes which most people can't experience directly, and you have to divide by another 100,000, and you get to the nuclear diameter. That's the nucleus inside of an atom, and you're still not there. You have to divide that by 1,000. And then you get to this 10 to the minus 18. And that's where the challenge is. And there are 2 challenges in this business that you can get to, and I'll tell you exactly what they are right now. The first challenge is you're going to be using light to make that measurement. And light has a wavelength of about 10 to the minus 6 meters. You have to get to 10 to the minus 18 meters. So you have 10 to the 12, a billion, I don't know the damn numbers, a million times a million, whatever that is. 10 to the 12, you have a factor of 10 to the 12 to go to do the experiment. That's your first challenge. And that's to measure with light such a small motion. But then you have another challenge. When you get done, those 2 objects that you have that are going to be measured to that precision can't be standing, they have to stand still enough. They can't be wiggling for other reasons besides the gravitational wave. And we'll talk about that a lot more in a minute. So first let me talk, both of those things turn out to be factors when we get done with it. And I'll get more to it in a minute. Those are both 10 to the 12 factors. We'll get to that. And that's where the challenge lies. And that's why it took 40 years to get there. Okay, so here are the people who actually made the first challenge work. This is the business of going from 1 times 10 to the minus 6, 10 to the minus 6 meters, to 10 to the minus 18 meters, using light as the way to do it. And there was a group at MIT, and this is the man actually over here, F.A.E. Pirani, who at that meeting in 1957 finally settled the argument. What could you do? How could you measure a gravitational wave? And he came up with a very neat way of not necessarily showing us that. He showed us how, if you take 2 particles moving in that jungle gym that I showed you earlier, and they're moving along a path That's the easiest path for them to move, the straightest line they can go on. In the fancy words of that field, those are called geodesics, the shortest paths in time and space that something travels. And you want to measure the distance between those things. You can do it in a way that is absolutely correct. And that's what he showed us, F.A.E. Pirani showed us. And based on that, I came up with, using that Gedanken experiment, turned it into a real experiment. And here are the basic ideas. I won't go through this diagram. I'll go to a more easy diagram to understand. But these are the principal ideas, and I'll show you better in a minute. But you make a device, there's a laser here, and one of the ideas was to float all these masses. They're all hanging. You don't do that with interferometers. People never did that before. They just don't hang. You don't hang interferometers. People put them on engine blocks to make sure nothing moves. Okay? So you hang all these masses, and the other thing is you take the light and let it bounce many times between the two. You build up the sensitivity apparatus that way. And the other thing is that you use a laser for the interferometer. That's not new, but in those days it was new. So that was a thing that was built at MIT. And we got some distance with that, but then a group in Europe, and the first group in Europe that really was, much better work than we did at MIT. They did a really beautiful job. And they had money, they had a lot of good, skilled people, was a group that was a group at the Max Planck that was run by Heinz Billings. And you can see him here. He was a computer engineer, this man. He invented magnetic core memory along with other people. And that's how he got support from the Max Planck Society. But he got interested in this idea of Weber's. And so you can see here is his bar, and he had worked on this thing, and he and a group in Italy were really one of the best people to show that Weber was wrong. They saw absolutely nothing, and they proved it to us. So they decided, what should they do next? And many of them said, let's make cold bars or do the next thing. But no, several in the group had read stuff that we were doing, and they said, why don't we do what the guys at MIT are doing, which is fine. And they did a much better job than we did initially, and these people all contributed. In fact, I'll just say what they are. We'll get back to that, but you'll see the drawing. But they contributed different ideas. For example, that the idea you make cavities. Now, this is the idea that you recycle light. We'll talk about that in a minute. That you hang every mass in the system. That you know how to do the optics right. And this, Lisa Schnupp was the person who came up with a very clever way of reading out the fringe, in the light fringe in the interferometer. Along with that was a group in Scotland. Now, they were first in Europe, but then a group in Scotland who had gone through the same history. They also had made a bar, found nothing, and they decided that interferometry might be a better way to do this. And this is a group around Ronald Drever, who then moved to Caltech after this. But his group invented various ideas. For example, Harry Ward invented a way how you align the mirrors, how you keep them aligned. Brian Mears came up with a very clever idea I'll show you in a minute, which is to add another mirror to the interferometer to change its spectral response. We'll talk about that. And then Jim Huffes just ran the group when Ron Drever left. He was a young man. All of these were students of Ron's. And so this is the group back in the 70s that actually came up with most of the ideas that went into LIGO. Okay? And this is actually the instrument that was built for LIGO that we built, and this is a schematic of it, and I'll show you the different pieces of it, so now you know a little bit about the interferometry from that animation. And I'll dwell a little on this. So here's the things you know about already. Here's the laser, there's the beam splitter, and there are these end masses that respond to the gravitational wave, if you want to choose them at that. They're doing the moving. Now you'll notice a whole bunch of other mirrors in here. Let's start with more simple parts of this. This mirror here makes this into an optical cavity. In other words, it is used to make the light bounce back and forth many times. And the same thing happens on this side. And what you do, you endeavor to do exactly what we did in that animation. You make it so they spend equal time, the light spends equal time doing the bouncing back and forth here as bouncing back and forth here. And as it leaks out of the system, the amount of change, well, the time that is spent is the same. So you come to the beam splitter, and here's the photodetector. So now here are these two mirrors we had said nothing about yet. This is the first one. That's much easier to explain than the other. This mirror that Schilling invented, as well as Ron Drever, is an idea that is pretty straightforward when you see in a minute how the ideas work. Remember, I told you that none of the light goes to the photodetector when you set this thing up. It's only when a gravitational wave comes along and moves this mirror in and that mirror out a little bit that you begin to see light at the photodetector. So where is the light going in that interferometer? The light's coming out of the laser, And it turns out it's not going to the detector, so it's all going back to the laser. That's what it does. Every bit of the light, except for what's absorbed by the mirrors. So what next is the idea was then to put a mirror right there. And if you put that mirror at the right place, and you make the transmission of the mirror just right, you have to know what to do what you're doing, you can do something very interesting. You can make it so that all the light that comes out of the laser, when there's nothing going to the photodetector, all the light comes out of the laser, goes through that mirror, and gets trapped in this system, and nothing goes back to the laser ever. And you do that by doing another interferometer between the light that would be coming back from the interferometer, going through this mirror, going toward the laser, and canceling that with a light that would go from the laser and be reflected by that mirror. There are two beams there that are going in the same direction, and you can cancel them by doing an interferometer again. So that's called a power recycling mirror. Very elegant idea. And that effectively takes the interferometer and makes it as though you have a bigger laser here. So what that does, for example, in advanced LIGO, you might get 25 watts out of the laser. In this little piece of the interferometer, there's no light ever going here. Forget about that. But there's something like 500 watts of light going around inside here. And then in here, there's a megawatt of light going back and forth. Megawatt, or maybe 3/4 of a megawatt. So you've done a very elegant thing with that mirror. You've trapped the light, and it only goes into the interferometer. And where does the stuff go? It goes to heating the mirrors. That's what it does. And that becomes a problem after a while. So now is this other mirror, which is actually much harder to explain. And what that mirror does is it takes the light that is there when these have been moved, and it takes it and it can reflect it back into the interferometer. And what I want not explain it. If you ask me questions about it later, I come to the stage later and talk about it, I'll tell you exactly how this works with another diagram. But you can change the way the interferometer spectrum works. In other words, how sensitive it is at each frequency by putting that mirror in. And in the initial interferometer, we didn't have that mirror. Where we ran LIGO for about 5 years, we didn't have that. That's now incorporated in advanced LIGO. Okay, so next step in this thing is getting advanced LIGO going. And advanced LIGO was a big deal. It was a $200 million project just to build it. And we'll talk about where it went, but you had 2 detectors, both 4-kilometer arms. Arms on those things were 4 kilometers. Very much the same as that drawing that I just showed you, the schematic, but with other things now which we have to be incorporated that reduce the motion of the mirrors, and we haven't talked about that yet. But this is the group, and why I want to show this slide, it tells you some interesting things about a big project. First of all, it turns out that Drever, here he is, and Kip Thorne and I tried to run this project, and we didn't know how to do it right. So it turns out that many committees said, you guys flunk. And we got a director named Robbie Vogt, who was an ex-provost of Caltech, who was a bit of a dictator, but he had the right instincts about how to get this thing going. And he got us through writing one of the most remarkable proposals that ever were written. It's a beautiful textbook on all the stuff that was in our heads that we hadn't written up. And we wrote it up. It took us almost a year to write this proposal. But it got the acceptance of the reviewers, and it got us the initial bunch of money to start building LIGO. And one of the clever things that Robbie Vogt did is he coupled, because his idea was, this is a very complicated engineering job to build this thing, and you better get the scientists who know what the complexities are mixed up with the engineers who know how to do it. Don't make engineers build something without scientific advice. And that's what he did for all the different contracts. For example, this group of people, well, these two, and I was the guy who worked with this guy, there was always a scientist mixed up with an engineer. For example, this is for the physical construction. This was for the vacuum system. And I worked with Larry Jones for the thing that was a very special piece of the vacuum, namely those big, long beam tubes, how to build them cheap enough so we could afford LIGO. And that was a very clever idea that Robbie Vogt had. So now I want to show you the very first detector that we built in LIGO and what the noise budget, what kind of things disturb it. And then you'll understand where the second piece of the hard problem comes from. Now this is a somewhat complicated drawing. This drawing has frequency down here, and it has strain here For example, this is 10 to the minus 25, 10 to the minus 23, 10 to the minus 21, 10 to the minus 19, if you can't read it back there. But it's not strain directly, it's the spectrum of the strain. It's how much strain per bandwidth. And now, the way to convert that into what I've just been telling you is to say, look, let's look at this point in the picture. Here's the performance curve for LIGO, the initial LIGO we built, and I'll explain a little bit what these curves mean in a minute. But right now, let's just take this point down in here someplace. It reads 10 to the minus 23, everything about here is 10 to the minus 23 strain per root hertz. And then you look at the frequency, and if you take a bandwidth that's equal to the frequency, you wind up with a factor of 100, but it's per square root of that, so it's 10. So you wind up that the best this instrument was doing is about 10 to the minus 22. It's 10 times 10 to the minus 23 in the strain that I was talking about with you earlier. That's how you make the conversion. But this is a way of showing how the spectrum depends on frequency. And for example, this piece, the thing up at high frequencies here, is determined by how well you can make the phase measurement of the light. And you need more photons. The more photons you have, the more light particles, the more power you have in the light, the better you can do this. So this will go down if we increase the laser power. On the other side of this thing, which is not important in this instrument, there's something very interesting. It's something called radiation pressure noise. And what is that? It becomes important in the advanced detector. What that is that if you try to increase the power, so you reduce this, it turns out this line is due to the fact that as you increase the power, you start pushing the mirror around. And the photons actually start pushing the mirror around with some noise. And that is, for those of you who know a little quantum theory, the Heisenberg microscope. All over. That was how the uncertainty relationship was developed. In other words, now you're talking about the Heisenberg uncertainty principle with a thing that is sort of 20 kilograms. That's what the mirrors were here. And quantum mechanics becomes important in this system because you're looking at such a very small motion.